Welcome to solverfy.
Here, we're going to use Faraday's law. And for part A, we can say that since the flux arises from a dot product of vectors, we can use one sign for the magnitude of the magnetic field sub 1 and sub 2, and then essentially we're going to use the opposite sign for B sub 3. We're going to choose the minus sign for the flux from B sub 1 and B sub 2, and then that implies essentially that we need to use a plus sign for the flux from the third magnetic field. So we can then say that the induced EMF, according to Faraday's law, would be equal to negative times negative 1 essentially. So negative 1 times the sum of the change in the magnetic flux with respect to time. This would essentially be equal to A times dB sub 1 divided by dt plus dB sub 2 divided by dt minus, again, the change in magnitude of the third magnetic field with respect to time. Again, we are choosing these sign conventions because we're choosing the minus sign for B sub 1 and B sub 2, or the magnetic flux of B sub 1 and B sub 2, and then we're choosing the plus sign for the magnetic flux coming from the third magnetic field. And at this point, we can just solve. So the EMF would be equal to 0.10 meters multiplied by 0.20 meters multiplied by 2.0 times 10 to the negative 6 plus 1.0 times 10 to the negative 6th minus 5.0 times 10 to the negative 6th. And then here the units would be Teslas per second for this term here. So we can say that the EMF is then equaling negative 4.0 times 10 to the negative 8th volts. And essentially the minus sign means that the effect is dominated by the changes in B sub 3. So we can then say that it's the current, essentially I, would be equal to the absolute value of the EMF divided by the resistance, and this is equaling 4.0 times 10 to the negative 8th volts divided by the resistance. R is going to be equal to 8.0 microamperes. This is the current again. Now, this is simply because this is found again, dividing the EMF by the resistance. This is simply according to Ohm's law. So we used Faraday's law to find the EMF, and then we're using Ohm's law to find the current. And then for part B, we simply need to use Lenz's law to find the direction of the current. And essentially, we can then say that the induced current is counterclockwise. That is the end of the solution. Thank you for watching.